Today we're going to take a look at springs. So, let's go over here. Spring. Generally, they're just pieces of metal that have been wound around some kind of form and then heated to treat them. And not all springs are created equal. We've got this kind of spring here, and then I've got this spring right here, which I can barely budge, where this one seems to move all over the place. So we want to investigate that a little bit on our way to talking about work and energy and power. And the way we're going to do that is by taking a look at Hooke's law. And Hooke's law relates the extension of a spring, so how much it stretches, to the force that is applied to that spring. Now, we're going to see some relationships. So I'm stretching it, applying a force and stretching it. And you notice that the spring keeps returning back to its original shape. So I stretch it out, boom, back to its original shape. And as long as I stay within a certain limit, that's going to be true. You'll notice that this spring is not so pretty. That's because some student who will remain nameless overstretch this thing, and once you overstretch it, the atoms of metal that are connected together in the spring rearrange themselves permanently, and that's called your elastic limit. So your elastic limit, when you exceed that, then the spring no longer goes back to its original shape. That's kind of outside AP Physics discussion. So we are always going to stay within the elastic limit, and we're always going to stretch it, but not far enough where we destroy it. Okay, we're going to take some data. I'm going to take this spring, and I'm going to hang it up here. And I want to know where the bottom of that spring is on the ruler right there. You could probably look from this camera angle and try and figure that out. But unfortunately, the camera is at a level down here, and it needs to go up like above my head. So you're going to have what's described as parallax error. Parallax error is when you look at something from an angle, you can get weird data. So in order to shut some of that parallax error down, I'm going to take video with my cell phone from closer up. So you can use this video just to get the general story, and then in the side there, I'll drop in pictures where you should take the real data. So right now, it looks like the bottom of that spring is somewhere around 2 centimeters, give or take. And I am going to hang one of these weight holders or mass holders onto the bottom of that, and we're going to see if that had any effect on the stretching of the spring. And it looks like, if we look at the very bottom of the spring now, that it's a little lower, maybe, I don't know, maybe like 2.5 centimeters ish. So what we're really after here is the force that is on the spring, and the force that's on the spring is coming from the 5-gram mass. So we want the force, that's 5 grams, so I need to convert the grams into kilograms, and then the kilograms into newtons to get the force on the spring. Then I want to know what the extension of the spring was. So I know that I started around 2 centimeters and it went to about 2.5 centimeters. So my extension for this 5-gram force was about 0.5 centimeter. So now we're going to take some data for real. I'm going to add in 30 grams so that in total, I now have 35 grams of mass hanging from the spring right there. So it's 35 grams total, which will give us our force. And I'm going to use a cell phone so we can figure out where the bottom of the spring is. Okay, and that appears like it's at 82 point something. You can take your data. So do your best to take some data off of that. And again, the mass that was hanging up there was 35 grams. Now I'm going to add 65 grams to this spring. And again, we'll take out the camera here, and we're in the 70 range now. And you can take data, see if you can figure out where the bottom of that spring actually is. Okay, your data is probably going to be a little bit rough. That's okay. That's why we take multiple trials of this thing. Okay, again, that was 65 grams. We're going to bump it up to 95 total grams, including the holder. Okay, so see if we can get an idea where that one is. Now we're in the 60 range. Looks like 65 something. See if it's a little better over here. Okay, I want to stop here for a second because you'll notice that I've been carefully lowering the weight. If I just added the weight and let it fall, the weight would do this. Now, this is called simple harmonic motion. It's a bouncing up and down, and we will study this in a couple of weeks. But for now, we want to keep this as simple as possible. And so you'll notice that each time I add a weight, I slowly lower it into the position that it will have its equilibrium. Okay, again, that was 95 grams. We're going to bump it up again to 125 grams. Okay. Now, if that's 60, we're 50 something. Okay, and our last data point, that was 125. The last data point is going to be 155 grams. Oops, sorry, 155 grams. See, give you an idea, some data there. Okay, so you have 5 data points, and you've got all the things that you need to be able to graph the force that is on that spring versus the extension, how much the spring has stretched from its original position. Now, before we do that, I want to show you one other thing about springs, which is, let's put here's the 65 grams back again. And if I hang it on this spring, it appears that, let's look at the bottom of the weight here. The bottom of the weight appears to be about 60 centimeters. Maybe a little more, maybe 61, something like that, 61-ish. Now, if I change springs, so I'm going to take this spring, which I said was pretty stretchy, and I'm going to substitute it for its twin. Whoop. This one's also pretty stretchy. So hang that one up there. And take my 65 grams. We were at about 61 centimeters last time. And now when I hang this one up there, whoa. Why is that?